Thanks so much. Thanks for the introduction. And it's really good to hear that you have many of the Orbitrap instruments. So yeah, my name is Kevin Yan. I'm a technical sales specialist at Thermo Fisher. Before my current role, I was an application scientist, also at Thermo Fisher, to develop different workflows to support proteomics. So I joined the mass spec world about like 7 years ago, and I've seen so many advancements in the last 5 years, especially with the launch of Orbitrap Astro mass spectrometer. We are in a very exciting era now. We can do so much with mass spec, and there are just so many to cover in a 15 minutes talk. So I'll be focusing mostly on the workflow that most people are applying, that is the bottom proteomics for protein identification and quantitation. But I would like to take this opportunity to invite you to think about what else can you do with mass spec. You can identify the protein, quantify the protein. You can also study the structure of the protein, the localization of the protein in the cells or in the tissue, protein-protein interaction, protein-ligand interaction. So how can you adapt the proteomics workflow of all these applications to your research to address complicated biological questions? So just want to walk you through the entire LC-MS workflow for bottom-up proteomics. Many of you are probably very familiar with this, but I want to make sure we are all on the same page. So for bottom-up proteomics, we prepare the samples. Mainly, we digest the proteins into peptides using protease, such as trypsin. The peptides, let me pull out my laser pointer. The peptides are separated using liquid chromatography to give you better sensitivity and coverage. The eluted peptides are analyzed on the mass spec, and the acquired data can be processed. Biostatistician will be introduced herein to extract meaningful insights to answer your biological questions. For today's talk, I will start with the LC-MS data acquisition. I want to talk to you about the label-free DIA analysis that you can do on an Orbitrap instrument. Following that, we will talk about the classic tandem mass tag or TMT-based isobaric labeling to achieve precise quantitation and to improve the throughput. After that, let's spend some time on sample preparation. I want to introduce you the potential solution to scale up your research to have a higher throughput in the sample prep. So many of you probably have done proteomics before, but I just want to take some time to ensure we are all familiar with the fundamental data acquisition on the mass spec. Here, I use Orbitrap mass spectrometer as an example. In the bottom-up proteomics, you will first acquire the MS1, the M over Z of the precursor ions, right? So ions will be guided through, analyzed on the high-resolution mass analyzer, the Orbitrap mass analyzer. After that, you will isolate specific or a specific range of precursor ions, right? Use this quadruple to isolate those ions, fragment them in the collision cells, then you guide the fragment ions back to the Orbitrap mass analyzer to acquire the M over Z of the fragment ions or the spectra of the fragment ions. With that in mind, there are two approaches in discovery proteomics, in bottom-up proteomics, the data-dependent acquisition, or DDA, and the data-independent acquisition, or DIA. In DDA, the mass spec will isolate specific precursor ions depending on the intensity, right? So you isolate them, you isolate the high abundance species one at a time, fragment those precursor ions, and then acquire the MS2 spectra of those precursor ions. In DIA, in contrast, you sequentially isolate the precursor ions in the predefined M over Z range. You isolate this big chunk of precursor ions and acquire the MS2 spectra of all those precursor ions, again, sequentially in the predefined M over Z range. There are different advantages in DDA and DIA, and it really depends on what questions you are asking, and that will lead you to decide if you want to adapt DDA or DIA in your proteomics analysis. For DDA, because you always isolate the high abundance species, it is very likely to be your peptides in the samples. So the acquired scans, the MS2 scans, is most likely to contain to have useful information, and that allows you to maximize the efficiency of MS2 scans. In contrast, in DIA, you always acquire the MS2 spectra of the precursor ions, regardless of its intensity. And that gives you the maximized reproducibility. Because in DDA, if you have something that's lower in abundance in certain samples, you might not have the MS2 spectra for that precursor ion in that sample due to stoichiometry. But this is not the case in in DIA, right? So you have the good reproducibility, especially when you have a logic cohort to study. This allows you to get the most reproducibility. Years ago, DI approach is computationally challenging because the complexity of the MS2 spectra. But in the last couple of years, many tools have been developed to analyze DIA results. You have Diane, SpectraNet, Chimeras on Protein Discovery, FragPipe, and so on and so forth. You can name it. Nowadays, this part of the workflow is less of a challenging, and we're seeing more people adapting DIA into their studies. Just want to compare DDA and DIA a little bit further. So the diagram you're seeing here for DDA, you can see that first you have MS1 scan, the survey scan, that tells you what ions are abundant in your samples in the elution window. Then you isolate those precursor ions to acquire the MS2 spectra, right? And then you move on to the next survey scan, and you might have different ions that are high in abundance. Then you isolate them, isolate the different precursor ions for MS2 spectra collection. In DIA, you sequentially isolate those precursor ions in this predefined M over Z range. You cycle it through, and then you go back and then cycle it through again. So this is the acquisition approach of DIA. In DDA, usually you apply isolation window, a narrow isolation window of 0.7 to 2 Thompson, or M over Z. In DIA, you probably will apply something higher, like 8 Thompson or higher. Another difference between DDA and DIA is the missing value. So in DDA, you will have missing value at random, but the missing value in DIA is often meaningful. Let's use this toy example of 9 sample study with 11 proteins as an example. So in DDA, you might get missing value. That could be because the samples are so low, or it just happened to not be sampled in this run, in this sample. So when you have a missing value in DDA, it's not always meaningful. But if you have a missing value in DIA, that is most likely due to the fact that this sample, this peptide, for example, this one, is so low, it's below the detection limit, and that information is useful. So that's a key difference between DDA and DIA regarding the missing values. And because you have less missing value to address, and the missing value is meaningful in DIA, that makes the sample, the data, the proteomics data more comprehensive. So to support our customers setting up LFQ DIA workflow on their Orbitrap instrument, we developed a velocity DIA workflow. It's a workflow that we have transferred to multiple sites on many different Orbitrap instruments, and it always works. So it's a easy to use LFQ DIA workflow if you're interested in transitioning from DDA into DIA. In this workflow, for the liquid chromatography component, we have the Vanquish Neo UHPLC system coupled with a micropack Neo column. The ions are ionized using the easy spray nano source. And we also have the Fans Pro interface, which is optional depending on the application you're running. For mass spec, this can be adapted to any of the Orbitrap mass spectrometers, the hybrid or the tri-bit systems. And the data can be analyzed using any software of your preference. The beauty of the raw data from Thermo is that it's probably always compatible with any available software, right? You can do that with Spectrum, Diane, Chimeras, MaxQuant, anything you want to use. It's probably gonna be compatible. So altogether, this is the easy to set up LFQDI workflow for your Orbitrap mass spectrometer. There, there are a few components I would like to introduce a little bit more because you probably haven't used it before or you're not familiar with. One of them is the MicroPack Neo HPLC column. So this column has the CAT material engineered as a micropillar on the column. And that gives you the best reproducibility and sensitivity because in this column, these micropillar are positioned or engineered to have a fixed distance in between. So unlike the packing material, where your packing material might distribute slightly differently depending on where you are in the column, in the micropack, you always have the fixed distance. What does that mean? So if you look at this, it means that your analytes will migrate, will go through the column very consistently, and that gives you better sensitivity because you have a very narrow peak and thereby very wide dynamic range for better quantitation. Another component I'd like to introduce is the FIMS, field asymmetric mobility spectroscopy, that you can hook up to your mass spec upfront. What it does so well is it filters out the certain precursor ions of a certain charge state. So if you have some contaminants in your sample, like the detergent residue from sample prep, those are probably gonna be singly charged. What FIMS does so well is it can filter out those ions, so it won't get injected into your mass spec. What does that mean? It means you first get better hygiene on your mass spec, so better robustness of your instrument. Also, if you have low abundance species, for example, single cell application, getting rid of those contaminants will give you much higher sensitivity. So if you look at the data shown here, this is 50 picogram of HeLa digest, and you can see the results with or without FIMS are day and night, right? So if you have low abundance species and you want to improve the sensitivity, we will recommend you to put the FIMS onto your mass spec. So this is the entire LFQDI workflow we would like to present you today. And we always evaluate our workflow using different samples. One is the HeLa digest. This is the golden standard most people are using. So we inject 200 nanogram of HeLa digest. That gives us the idea of the protein coverage and also the quantitation precision between different technical replicates. We also like to investigate the quantitation accuracy using the 3-proteomics. That allows us to understand the protein coverage when you have a more complex samples, and also if this workflow gives you the accurate quantitation, which is extremely important if you're studying biological questions. For 3-proteomics, we have two mixtures. In mixture A, we have 325 nanogram of HeLa digest. On top of that, we spike in 100 nanogram of E. coli and 75 nanogram of yeast. For mixture B, we also have 325 nanogram of HeLa digest, but we spike in 25 nanogram of E. coli and 150 nanogram of yeast digest. That gives you, between sample A and sample B, a ratio of 1:1 for HeLa, which reflects the majority of your proteome when you're comparing different conditions. A ratio of 4:1 for E. coli and 1:2 for yeast, respectively, and that allows you to evaluate if you can capture the differential expression between different samples. What we're expecting from a good data is something like this. So this is a box plot. And between sample and sample B, we expect that the results, the observed median ratio, to align very well with the expected ratio. We also expect a narrow distribution because that shows that the majority of the proteins can be quantified accurately. So With that, let's first look at the experimental setup for our LPDIA workflow on the Orbitrap instrument. We have different throughput, and I'm gonna use this 30-minute gradient as an example. So we basically have a step gradient, just like most of you are doing. And if you haven't used a Vanquish Neo before, you'll probably notice that the equilibration is missing here. And that is because on Vanquish Neo, you set up the equilibration based on the column's specification. So you'll tell the system, the LC, what's the diameter of your column, what's the length of your column. It will calculate the column volume. And based on that, you set up how many column volume you want you want LC to equilibrate, right? So you don't have to do that calculation yourself anymore. You don't have to worry about if you're using enough volume to equilibrate your column. We make this easier for you. Also, we develop different throughput depending on to support your different needs. We have the 60-minute gradient, 30-minute gradient, and also the very high throughput 9-minute gradient on the Orbitrap instruments. So here's a chromogram of different gradient, and as expected, the longer the gradient you use, the more protein ID you're gonna get, right? So it's all about what is your sweet spot here. We can support all kinds of gradient that you might want to run. Let's go a little deeper into the mass spec setting, especially for the DIA or the MS setting. So in this workflow, we have a precursor mass range of 400 to 900 m/z. We can go higher, but that means you'll take longer time to cycle through the range. And we found that 400 to 900 is a good range to give you the coverage and the points per pig for quantitation, especially with that fact that most of peptides are probably in the range of 500 to 800 range, right? So we can capture most of peptides with this range. We test different isolation window, and we found that 12 Thomson is the sweet spot. It gives you the good coverage. In the meantime, good quantitation because you have enough points per peak. For the resolution on Orbitrap, we use 15,000, which is good enough to get the high quality spectra for MS2. If you go higher, you'll have higher quality of spectra, but it takes longer time to complete the cycle, then your quant is probably going to suffer. So altogether, this is a combination of parameters that we tested, and it works very well so far. For ultra high throughput, we tweak the parameters a little bit. So if you think about proteomics, you have the coverage, throughput, and quantitation, the three pillars of proteomics. And most of the time, you just cannot have them all. So when we want to have a high throughput, like 9 minutes gradient, the coverage or the quantitation is going to get hit a little bit. And with that, we developed two different methods. One is to maximize the identification to give you the best protein coverage, but your quant is going to suffer a little bit. And the other one is to max out the quantitation, even at high throughput, but you'll identify less peptides and proteins. The main difference of these two methods is first, the precursor mass range. For max ID, we set it to 400, 800, still kind of wide and allow us to capture the majority of the precursor ions. But for mass quant, we narrow it down further to 650 to 770. So it's pretty narrow. But if you're doing a discovery proteomics for protein quantitation, not peptides, if you're interested in protein quantitation, this still gives you enough peptides per protein to quantify. Another difference is the Orbitrap resolution. For max ID, we increased that to 30,000 because at such short gradient, the spectra gets very complicated, and we increase the resolution to get higher quality of the MS2 spectra for complex such a complex condition. For mass quantitation, we keep it as 15,000 to get better points per peak, and that will, together with the narrow mass range, give you still 4 to 5 points per peak, even at such a high throughput, and thereby get better quantitation. So we talked about the sample we're gonna run and the LCM is set up. Now let's look at the data of our velocity LFQDI workflow. So first is the HeLa digest, 200 nanogram of HeLa digest with different throughputs. We have 60 minutes, 30 minutes, 9 minutes with max identification and max quantitation. You can see that as expected, 60 minutes gives you high coverage, over 6,500 protein groups using spectrum out. For 30 minutes, we can still get about 6,000 proteins, and this is on the Orbitrap Explorers 480. For 9 minutes, very high throughput, we can still get close to 5,000 proteins, even at such short gradient, if we use the max identification methods. For the max quantitation, the IDs gets suffer a little bit, right? You can get only close to 4,000 proteins. But if you look at the quantitation precision, it clearly shows that if you use the 9-minute max quant methods, the CV is still below 8%. So that is the quantitation you can still get with such a high throughput. If you use the max ID methods at such high throughput, yes, the ID increase, but the CV is gonna be 11, 12%. It's not bad, it's still below 15%, which is acceptable in this community, but just not as good as this one, right? For 30, 60 minutes, they're 5 to 6%, pretty consistent. So altogether, what we're trying to show here is you have different options. You can run 60 minutes, 30 minutes, or even higher throughput. Depends on what you need to run, what data you're trying to get. Orbitrap instruments provide you the flexibility. Similar results were found on different softwares such as Chimeras with Proteome Discoverer or Diant. And what I'd like to highlight from the Diant result is we can obtain over 7,000 proteins in a single 60 minutes injection from 200 nanogram of HeLa digest. So this is the sensitivity of the Orbitrap instrument you can get when running an LFQ-DI analysis. Is there a way to further boost the coverage? Yes. So one way you can do that is to run a library search. So you can build a library. Here we build a library using the 13 cell lines, single injection 13 cell lines to build a library. And we search the result, the same results against the library. Compared to direct DI search, you can see that with the library, you can get even more protein identified and quantified. Another thing I like to point for library search, if you have not done it before, is it takes way shorter time to complete a search. So instead of a couple hours to complete a direct DI search, it only takes like 20, 30 minutes to complete a search. So it saves a lot of time. Think about that. Think about a situation when you have a very exciting project where you're running and you want to see the results really quick. If you have a library, you can see the results in less than an hour after you acquire the raw data on the Orbitrap instrument. Or we can just load more on the column and that will give you more coverage as well. So I tested 500 nanogram HeLa digest with 60-minute gradient, and we were able to identify 8,000 protein groups from a single injection. So again, that's the sensitivity of the Orbitrap instruments. We also tested the quantitation accuracy from 3 proteomics. Just to recap, we have 3 different proteome for HeLa. They're unchanged between the 2 mixture, which should reflect the majority of your proteome between samples. We also have E. coli and yeast that give 4 and 2-fold difference between samples respectively to reflect those that has higher or lower fold changes. One thing that impressed me right away when I saw the result is with 3 proteomics, the complex proteome on the Orbitrap Explorer 480, we were able to identify over 10,000 protein groups using a 60-minute gradient. So that the kind of coverage is what I was really impressed by Orbitrap instrument and why I still love the Orbitrap instrument. 30-minute gradient, you get 9,000 proteins. For 9-minute gradient, you can still get over 6,000 proteins. But identification is not all. More importantly, is the quantitation. Can we accurately quantify those proteins? So here's a box plot from the 30 minutes gradient as an example. You can see that the observed ratio pretty much sits on the expected ratio, right? And the box is so narrow. So this reflects that we were able to quantify accurately the majority of the protein in all the three species. This is true for longer gradient, 60 minutes, or shorter gradient, 9 minutes. So together, I hope I've shown you that Orbitrap instrument allows you to accurately capture or answer the biology questions. Want to give you a study as an example. We have this collaboration to study the mouse hyperoxia. So we have mouse treated with hyperoxia, or denoted as HO, or room air as a control, RA. The collaborator dissect the lung out from the mouse. We process the samples into peptides and run them on the Orbitrap Explorers 480. So first, we were able to identify over 6,000 proteins in this study, and among them, 97.7% of protein groups were identified in all runs. So that is the reproducibility you can get when running LQDIA workflow on an Orbitrap instrument. If we look at this PCA plot, you can see that, so on your left-hand side is the hyperoxia treated mice, either male or female, they're clustered together. On the right-hand side are the control. Again, you have the male and the female, and they're clustered together. It really shows that the main driving factor of the differential proteome is the hyperoxia treatment. When conducting PCA, we also found that 80% of the data can be explained by the first three components, and that shows you the effectiveness of accurate quantitation when you're tackling with biological questions. Here's a volcano plot showing that many of the proteins are up or down regulated upon hyperoxia treatment, either in male on your left-hand side or female on your right-hand side. So I'm not a biologist, right? So I don't really know what are those what are those proteins, but I found that many of them are mitochondria related proteins. And according to our collaborator, this is what they're expecting. So this is something that shows that Orbitrap instrument captures the biology using a high throughput LFQ workflow. We also compare the hyperoxia treatment or room treatment, like room treatment on your left, hyperoxia treatment on your right, between male and female, and we didn't see much difference. So this serves as a good internal native control, meaning that those proteins that are not supposed to show difference is reflected in the data set. Moving on, as you many of you have not probably have known that we launched the Orbitrap Astro Mass Spectrometer 2 years ago, and we can also apply the label-free quantitation using DI workflow on the Orbitrap Astro Mass Spectrometer. In Orbitrap Astro, you can get the coverage, quantitation, and the throughput now. You can get all three of them. You can run it so fast that still give you the good coverage, deep coverage, and accurate quantitation. So the example I'm going to show you today is a project on targeted protein degradation with Protect compounds. So targeted protein degradation, or TPD, is right now a very important small molecule drug discovery approach. In this approach, we use a small molecule like Protect to breach the targeted protein with E3 ligase to promote its ubiquitination and thereby degradation. And people like the approach because this is a new way to target those undruggable proteins, and you're using a system that already exists in the cells to drive the degradation of those harmful proteins. For example, in this paper, they studied the Protect ARCC4, which can drive the degradation of androgen receptor in prostate cancer cells with high specificity and efficacy. So to drive those kind of study, the discovery of Protect compound or other protein degrader, mass spec is really important because most of the time we need to do a screening of those compounds. We're talking about thousands of compounds to screen, and we want to know which compounds are the right lead. How do we achieve that? How do we screen those compounds from mass spec? Well, you need the throughput with depth, you need accurate quantitation, also you need the reproducibility. To support this aspect, we develop a DIA-LC10 mass spec workflow on the Orbitrap Astro mass spectrometer. So we have the Vanquish Neo UHPL system using the trap and elute mode to promote the throughput. We have Orbitrap Astro mass analyzer running with narrow window DIA that gives you the good coverage, the big coverage, even at high throughput. And our raw data, again, compare with almost any software in the market. To conduct a proof of concept experiment, we treated the VCAP cells with different concentration of ARCC4 for 4 hours. And after that, we lyse the cells and prepare those samples, digest the samples on the Celeron platform for automated sample preparation. Before we even look at the results of the Protect study, we first want to evaluate our workflow using, again, the 3 proteomics. So we tested 4 different throughputs to fulfill the needs of different people and also different purpose. So we have higher throughput, 180 or 300 samples per day, which is good for the initial compound screening. Also, we have 24 or 60 samples per day, which can be used for the following validation when you need to get more in-depth coverage. We test the quantitation accuracy using the same 3 proteomics, and you can see that regardless of the throughput, the observed ratio and the expected ratio are aligned very well, and the box again is very narrow. So this gives us a confidence that the different throughput we are applying here gives the accurate quantitation. So with that, we inject the Protect samples onto the Orbitrap Astro mass spectrometer, and this shows the coverage of protein groups and peptide groups at different throughputs. So for protein groups, you can see that even at 300 samples per day, we can quantify about 8,500 proteins. This is a deep protein coverage at such a high throughput, and it works very well for the initial compound screening. Later on, if you need to do a validation, you can run 60 or 24 samples per day, and that gives you over 10,000 protein coverage. So if you need to validate the on-target and off-target effect of your Protect compound, right, you need to quantify more proteins, then you can run a longer gradient for those filtered compounding from your initial screening. This is a Violin plot showing the CV of different throughput. All of them gives you a CV less than 15%, highlighting the quantitation precision from Orbitrap Astro mass spectrometer. So is androgen receptor degraded? Can we capture that? Well, yeah, you can see that from the volcano plot. Regardless of the throughput, we found androgen receptor being the predominant proteins degraded upon 500 nanomolar of ARCC4 treatment. And this compound was previously shown to be specific and potent. And yes, our Orbitrap Astro mass spectrometer captures that even at 300 samples per day. So this is the quantitation performance and the scanning speed you can get from Orbitrap Astro mass spectrometer to discover biology. We calculated DC50 and found that they are similar across all the throughput. So we can get consistent quantitation if even if you run it at 300 samples per day. So that will conclude the label-free DI analysis I'd like to show you today. You can do that on Orbitrap instrument very well. If you have an Orbitrap Astro, you can get all three pillars at once. Following that, I'd like to talk about the TMT-based isobaric labeling to multiplex your samples in a single injection. So why do we want to multiplex? Well, a major challenge when you can increase your sample prep throughput is that you don't have enough instrument time. And if you don't have an Orbitrap Astro mass spec, but you're still looking to run hundreds of samples, then it's gonna take forever to complete a study. One approach to address that is through multiplexing. That is, you combine all the samples together into a single one, and you run them all at once, right? So think about how much time you can save through multiplexing. Another benefit of multiplexing is you can have multiple conditions. You can have multiple control for multiple condition all together in a single sample. So this allows you to test multiple conditions and have multiple replicates in a single proteomics analysis. Other advantage of multiplexing is you get better reproducibility. If you can recall earlier when we talked about DDA, a key drawback is the missing value, right? But there are some experiments you still want to run with DDA. Like if you want to study the PTM, when you want to have a high confidence of spectra, you want to clean spectra, then you want to run DDA over DIA. Multiplexing allows you to have high reproducibility between samples when you're running DDA. So all these are the benefits of multiplexing. In the multiplexing approach, one of the most commonly used is the so-called tandem mass tag. So you tag those different proteins with different tandem mass tag or TMT that give you the same mass after tagging, right? So you have one single peak in the MS1. But after fragmentation, the TMT is going to release different reporter ions, and you can achieve relative quantitation based on the intensity of those reporter ions. So here's the first commercially launched 6-plex TMT in 2008. So we have 126 to 131 of reporter ions after fragmentation. The magic to this isobaric tag to TMT is that it has the mass reporter ions that incorporates increasing number of heavy isotope, which is offset by the decreasing number of heavy isotope. And you have the amine group to react with the amine on the N-termini and the lysine. So you can tag your peptides after trypsin digestion. A few years later, we further expand that to TMT 11-plex. So we have the carbon-13 heavy isotope swap for nitrogen-15, and that gives a delta mass of 6.32 millidalton, which can be captured, which can be differentiated on high-resolution mass analyzers such as Orbitrap. And then we further expand that to 18-plex for higher multiplexing and also for improved fragmentation. And if you're following the proteomics world, you'll probably notice that we also launched the deuterated TMT ProTags last year. So in this series, we have the deuterium tag that gives you a 2.92 millidalton of mass difference, which is very, very small, but it can still be resolved on high resolution mass spectrometer, such as Orbitrap. So together, combining the TMT Pro and the deuterated TMT Pro, now you can have together a 35-plex. So think about how many conditions and replicates you can test now in a single batch of LC-MS analysis. So there are several applications that we found people are still applying TMT and DDA over DIA. That includes chemoproteomics, especially for activity-based protein profiling. TMT-based approach is the golden standard in the industry. single cell, you can have a boosting channel to improve the sensitivity. And cellular thermal shift assay, in this assay, people like to have all the points to draft the curve in a single injection. So you can apply 10 to 16, 18 to get the curve from a single injection. And they call this like a self-controlled, self-contained experiment, right? So all these approaches are where TMT still driving the discovery. If you're interested in doing TMT, we have different formats of reagents that you can purchase, you can get. And I really recommend getting this platform if you don't have a lot of samples to run. So we've seen people reformat the bulk reagent from the glass vial into 96 plates to label more sample sets for future studies. And we see the need. So we also launched the ready-to-use 96 plate. We have the 10, 11, 16, and 18 plex reagents available so far. If you are interested in the deuterated series, we have the 32 plex on demand. So if you're interested, feel free to reach out and we can customize the plate for you. So if you get this plate, you'll have the label on the back, on the pouch, right? It tells you which well has which reagent. You just need to spin it down and there's aluminum foil on top of it. You can tear it up, you can just poke through it to label your reagent. And this is because you don't have to reuse the reagent. It's for one-time usage, so it gives you the stability, easiness to adapt TMT onto your research. All right. And at the end, just want to touch base really quick on the sample preparation and the potential solutions that Thermo Fisher can provide. So many of you probably have done this before, but just want to walk you through the process again, just ensure everyone's on the same page. So for bottom-up proteomics, you have the samples either from cell line, tissue, any sources, right? And you just extract the protein out, lyse the cells, extract protein, and then you'll probably do a reduction calculation to break the disulfide bonds. After that, you conduct protease digestion, where trypsin is the most commonly used. Then you'll have the peptides that could be subjected into the mass spec for LC tandem mass spec analysis. You can do this manually, and I've done that a lot when I was in my grad school. But then if you are expanding this into the larger cohort study, you want to automate the process because now the mass spec can do so fast. You might want some robotic arm to take care of that. And we have two solutions at Thermo. We have a Celerum, which is a liquid handler. We also have the Kingfisher magnetic beads-based platform that allows you to do enrichment or cleanup, etc. So this is a Kingfisher, and we have the EasyPap magnetic sample prep kits that you can do a peptide cleanup, so you don't have to do the desalting like on stage tip or zip tip manually. You can automate this process using the magnetic beads, and that gives you higher throughput on the sample prep. You can also do this and add a protein cleanup step like the SP3, right? So you can clean up the proteins, also automate this process, and after that, you just add in the digestion, the reduction, acquisition, digestion solutions afterwards. So Kingfisher is a partially automated process, but it's at a much affordable cost. This is a way affordable instrument, and it saves a lot of time if you want to automate the sample prep process. All right. So just want to conclude. I hope today I've shown you that the LC-MS data acquisition for label-free data analysis on the Orbitrap or Orbitrap Astro Mass Analyzer, mass spectrometer. Also, the TMT-based aspirate labeling from the 6-plex up to 35-plex. You can do multiplexing to improve the throughput and quantitation precision in your DDA analysis. For sample prep, we have the Kingfisher to partially automate this process, and this could be used for other applications as well, such as immunoprecipitation, or if you're doing any plasma work, it can be used to enrich the EVs, right? So there's a lot of flexibility. And with that, I'll be happy to take any questions.
Does anybody here have any questions?
Okay, if nobody asks, I'll have
Okay.
one general question. So this is amazing. I'm happy to see you can measure like over 12,000 proteins. That's amazing. My question is, how do you compare yours with like Olink, other platforms like Olink, SummerScan, in terms of the sensitivity, reliability, and validation? Like the reason I'm asking is we have a lot of samples want to do proteomics with. So I'll be checking a lot of different platforms, and I even send samples to Sam to do a pilot test to see how many proteins we can get. So the problem is like Olink and SummerScan, they don't even colorate. They measure complete different things. Their peak coloration coefficient is 0, means like they're not colorated at all. So once we have to stick with one method, otherwise you cannot like replicate your results at all, especially for like a longitudinal study, right? So how's yours like compared to like, let's see, Olink and SummerScan? Like the coloration, the reliability, and the validation, like
So that's a good question. And this is a question for modern technology because Olink certainly wasn't really mature till 2 years ago. But it's definitely a very important technology now for proteomics. So I have not compared my results with Olink, to be honest. But what I found is there's not much overlap, or there's a minimal overlap between the results you get from Olink and mass spec-based proteomics. In other words, to us, these two approaches are sort of complementary. If you put these two together, that will improve your coverage even better, right? And in terms of quantitation, I come from mass spec world, so I trust the results from mass spec better because I can see the raw data and I can see those fragment ions. But it's just my opinion. Olink uses antibody to amplify the signals, and I'm not familiar with the technology good enough. I don't know how they detect the LQ, LLD after amplification. So that's kind of the question I'll ask them. How do we evaluate the quantitation accuracy from that new technology?
yeah, okay, thank you. So basically you're saying the mass spec does not correlate with Olink. And Olink does not correlate SummerScan. How about mass spec and SummerScan?
Yeah, if you look at a paper published by Josh Kuhn recently, right, he compares different technology for plasma proteomics, and it clearly shows that Olink and other approaches does not have that good overlap, which is good because if you adapt to a platform together, you can answer more questions.
That's good. So once we found, we do biomarker discovery, once we found a biomarker, are we able to validate those with like a regular biopsy, like ELISA, like antibody based?
Yeah, so once you identify a biomarker, right, you want to validate them. There are different approaches. You can use the different methods like antibody-based approach, or you can do a even deeper validation of mass spec. So you can do absolute quantitation. We have the stellar mass spectrometer, which I did not introduce today, but that mass spec is good for targeted proteomics, and you can get like synthetic stable isotope labeled peptides, do a titration curve to understand what's the quantity of this biomarker, of this protein, or these peptides in the samples. So there are different ways to further validate your discovery proteomics.
Okay, thank you.
Yeah, I think I'll add to that too, that at least for me, and I come to this fight as a mass spectrometrist, so I'm gonna, err on that side. You can look at mass spectrometry data you can look at the raw data, and it gives you some confidence in the call that's made. And it's something you really can't do with the O-Link or the SOMA methods. You get a data output, whether it's on a graph or a cell in an Excel spreadsheet. It's a number. You get numbers out of the mass spectrometry data too, but you can always go in and evaluate. Do I feel like this is a real measurement or not? And so that that comfort. Now, granted, when you're identifying 10,000 proteins, that's the last thing you want to do, right? Is go through and look at all these, but you have the ability to do that, and I think that's true for the validation as well. And I think some of the reasons that the correlation's probably not as good is that some of the antibodies are likely raised against proteins with some specific PTM fingerprint. And that may or may not correlate with the overall protein abundance that you're going to measure by mass spectrometry or maybe even SOMA. And so, they very likely are measuring something because it's fairly reproducible. What you're actually measuring is not as clear. And so it's kind of like a Western, right? And we get this asked a lot. I'm surprised it hasn't come up today. Is that, is the, what's more sensitive, a Western blot or the mass spectrometer? Yes is the answer, right? Whichever one you want. If you have a great antibody, it's going to be better than a mass spectrometer because it's going to be as sensitive and more selective. For most things, the mass spectrometer wins hands down, but there are those antibodies that are just great antibodies and they're going to win. And so it's those things that SOMA is going to detect that you're not going to detect with another method but you don't know exactly what you're measuring. You're measuring something, but you might be measuring, one specific glycoform on one protein or a glycoform that's been cleaved on a protein. And so there's ambiguity there, but for targeted validation and follow-up, I think there's no question that the mass spectrometry is the way to go because you can, as you mentioned, you can spike in a synthetic, stable isotope labeled peptide and compare. Okay, I can set a titration curve and I can actually get a true, limit of detection, limit of quantitation, like has been done in analytical chemistry for 50 years. You can do that with a peptide. And that's something you really can't do with SOMA or O-Link.
Thank you.
Okay, and Mike has a question on Zoom also.
So I just was curious from Kevin that I mean I'm familiar with the various DIA programs like Diane and Spectronaut, and I was just interested to see Proteome Discoverer on your list, and how well does it work, and is it competitive with those other programs?
Yeah, so like we have the Chimeris node on Protein Discoverer. I'll say it's comparable with other program. One thing I like to mention about Chimeris is like if you have already a system, right, we can automate the sample process as well. Doesn't mean you have to use Chimeris with Protein Discoverer. You want to automate the sample analysis, but it's some solution we provide from Thermo. People like to use Diane because it's free for academia, right? And it works very well. Like it's fast, it gives you the accurate quantitation, it gives you the coverage. I like Diane. The downside is you need to be familiar with data analysis because you get a single TSV output from Diane that gives you intensity of different proteins, right? So you need to know how to process those data. Spectronaut is somewhere sitting in between. It has a good GUI and it helps you visualize your data, but it's not free. So to me, it's something sitting between Diane and PD with Chimeris. With Chimeris on PD, you can do a lot of data visualization and extraction. With Diane, you can do any, but it's free and it's very fast. And Spectronaut is, in between these two.
Thank you.
All right, that looks like that's all the questions we got. Thank you, Mike, or Kevin, sorry.
Thank you, everyone.
Thank you, Kevin.